Afternoon, ladies and gentlemen. KS Jammuwal on virtual mode from Jammu. This is my privilege to address this August gathering on the topic Tunneling in Himalayas and role of engineering geology in the construction of major civil structures related to transportation and communication projects as well as water sources development projects with special mention of Chenani Nashri Highway Tunnel in Udhampur district of Jammu and Kashmir and Afghan-India Friendship Dam in Herat province of Western Afghanistan. I remained associated with these two projects right from their investigation stage up to their completion. Prior to the Chenani Nashri Highway Tunnel, I was assigned for Afghan-India Friendship Dam by the Union Ministry of Water Sources to render the geotechnical advice for that project. I remained associated for about 10 years with that project till its completion. And after that, I was assigned for Chenani Nashri Highway Tunnel by the Union Ministry of Surface Transport and National Highways as a key professional to supervise and review all the geological activities being carried out by the geologists of National and International Company of Latin Australia in association with Welspun Company of New Zealand. I worked for this project for about 5 years till its completion and now share with you my experience during the construction of these two vital projects of international standard, one in Himalayas in our country and other one is in Hindu Kush Himalayas, Hindu Kush mountain ranges of Afghanistan. Himalayan ranges, as we know, these are the youngest mountain system in the world. These have not yet attained their stability by virtue of their tectonic and dynamic basement with number of deep-seated lineaments, regional faults and thrusts in longitudinal as well as in transverse directions, thus dissecting these ranges into number of unstable blocks. And the status of these blocks has been further deteriorated by frequent visits of the earthquakes causing progressive instability. So, with such structural complications, the construction of major civil structures in these mountains, such as tunnels, dams, or highways, is a cumbersome task for geologists as well as for engineers. And to provide the stability to these structures is a joint and challenging responsibility for both the professionals, and in the absence of any one of them, these structures cannot be considered stable for longer period. Thus, a perfect coordination between the engineering geologist and civil engineer is the most essential requirement for successful construction of such structures, not only in Himalayas, but in any mountain system in the world. I remember the textbook on the principles of engineering geology and geotechnics, which I had read in the final semesters of MTech course about 50 years back, was co-authored by Karnine and Judd. But I did not know that Karnine was a civil engineer and Judd was a engineering geologist. This is very useful book for geologists as well as for engineers. Geologist learns the engineering characteristics of the rocks and engineer learns the geological properties of the rocks, and their combined knowledge is very helpful during the construction of the major civil structures in the field. I admire this book and consider it as a Bible for the engineering geologist because it covers all the aspects of the engineering geology. Basically, engineering geology differs from the general geology in scope. It may be defined as a branch of human knowledge that uses the geological information combined with practice and experience to assist the engineers in the solution of the problems related to the construction of major civil structures like dams, in which such knowledge is applicable. Now, while constructing the dams, a depth more than 300 feet is practically never exceeded, and our construction stage activities remain confined only within the upper thin layer of the earth crust, which is 10 to 20 miles in thickness. But the geological advice is needed right from the investigation stage of a structure up to the causes of its failure. Even the geological advice is needed during the sudden occurrences of the natural disasters such as earthquakes, tsunami, volcanoes, landslides, avalanches, and these things are frequently occurring on the surface of the earth and warrant the service of the engineering geologist to render the geotechnical and techno-economical treatments for these disasters. Uh, but I have observed that there seems some misperception, even in responsible quarters, on the role of engineering geology and its present day importance as a branch of scientific inquiry. A wrong impression seems to be lurking in the minds of the people that the subject of engineering geology is confined only within the project area and it has a narrow vision of wide field of geology. But this is not correct. I wonder, when a tragic earthquake shakes up the land or tsunami strikes, an inference is immediately drawn that there is something wrong with the geological education in our country that allows such things to happen without giving us warning. So much so, even the editors of some leading journals like Current Science have gone up to the extent of condemning the subject for not predicting the earthquakes. These critics have probably forgotten that the existence of our present day civilization is the result of prolonged painstaking labor of the earth scientists who with their traditional methods have provided minerals, metals and power energy which have established a very strong platform for further modernization of our civilization. I react on the comments of some critics regarding the prediction of the earthquakes. And this has reminded me also one statement which was given by a famous German scientist come philosopher Kant just after the disastrous earthquake of Lisbon in 1755. He said, "Look, gentlemen, earthquakes can neither be stopped nor can be predicted by constructing temples and churches. Instead, we have to delve very hard to know the causes which create such crises on the surface of the earth." This was the day when science was born on this earth, when earthquake engineering was born on this earth. I candidly admit that we are unable yet to predict the earthquakes, but then it is not only in our country, it is a universal phenomenon. Of course, we have discovered how to protect ourselves from them up to certain extent. See, we cannot direct the wind, but we can definitely adjust our sail accordingly. In fact, whenever a tragic earthquake shakes up the land, then according to principle, prevention is better than cure one must follow. But unfortunately, the occurrence of the earthquake is so quick, so sudden, and for short duration that this does not allow us to act wisely at that point of time. God forbid, if an earthquake occurs at this point of time, what will be our reaction? We all will be in panic, rush out of this hall to protect ourselves from the fall of structures on our head without knowing whether it is a good or bad act on our part. Friends, millions of people have died within minutes, along with massive destruction of the structures worth millions of rupees. I am reminded of the world's most tragic earthquake which occurred in central China in 1557, killing 8,30,000 people within minutes. And majority of them were those who ran out of their houses and became the victim of the fall of structures over them. By the way, the strongest ever recorded earthquake till date occurred in 1960 in the Chilean off coast of South America. Its magnitude was 9.6 on Richter scale, and its epicenter in the Pacific Ocean. Had it been on the land, probably entire South America would have been finished. Well, research work in this field is going on, and maybe someday we will be able to predict them exactly, but till then, we have to face them like that only. The importance of engineering geology was seriously recognized in 1928 when St. Francis Dam in South California failed with tremendous loss of life and property worth millions of dollars. This dam was constructed in 1926 and provided service only for 2 years, and in 1928 it failed. This was about 205 feet high dam, masonry dam, gravity dam. Its base width was 175 feet, crest of the dam 16 feet. It was given to understand that no detailed geological investigations were carried out for the foundation of this dam, and dam was constructed on a faulted contact of mica schist and conglomerate. Conglomerate is a very hard rock, but only in dry conditions. In dry conditions, we have constructed many tunnels in this rock without creating any problems. Even entire Jammu city, old Jammu city, is located on this conglomerate boulder bed of shivalik rocks, and we have cut the slopes of conglomerates even vertically to construct the national highways, and it did not pose any threat to its stability. I will quote one example of a tunnel on Chandigarh Kangra highway. Near Kangra, there is one tunnel of about 200 meters in length in this conglomerate rock, and it is intact and have been standing for the last about 100 years without any support system and without any shape. It's not a circular or semicircular or uh, square, rectangular or horseshoe, irregular crown and irregular walls. Once I was traveling with uh, one Spanish geotechnical engineer, and when we crossed this tunnel, we made a brief stop. He was surprised to see the configuration of this tunnel from outside and as well as from inside the tunnel. He said that probably this tunnel has been excavated by semi-skilled persons with handy tools and without deploying any machinery. But the tunnel is intact. So this is the role of conglomerate rock in dry conditions. But under submerged conditions, as is the case in St. Francis Dam, at the foundation of this dam, within 2 years, this conglomerate rock has been disintegrated into loose sand and rock fragments. With the result, it made a free flow of the reservoir water below the dam body, destroyed the dam within hours, and caused severe loss of life in the downstream. Engineering profession at that point of time realized that even if we provide a very best design to a structure like dam, this cannot be considered safe unless we involve geology in it. We have to implement the applied aspects of the geology along with exploration program to understand the surface and subsurface rocks, their physical strength, their geological properties, their engineering characteristics at the time of investigation stage, and then monitor these results till the completion of the structure, or even beyond that also in most of the cases. Geological, with such observations, the engineers thought it economical to retain a geologist at the project site rather than to face the consequences of the dam failures later on due to unforeseen conditions. So in this way, the profession of engineering geologist appeared on the scene, and today it is needless to mention that all the major civil structures in the world of water source endowment and in the world of the transportation and communication projects are being constructed with fruitful geological advice to provide them a long, healthy life. And this is not the casual requirement, but an absolute necessity. It goes without saying that for full industrialization of any country, for the continuation of our civilization and its further development, we need three fundamental bases: exploitation of mineral wealth, exploitation of power energy, and a network of transportation and communication projects. All these three constituents, when put together, form a solid platform from where a geologist looks for mineral wealth and an engineering geologist looks for the solid foundation for the civil structures. So professionally both are geologists, but their line of operation is in different directions. A country is prosperous if it has exploited fully its mineral wealth, if it's if it has exploited fully its power energy, and if it has an excellent system of transportation and communication projects. Friends, formerly the richest countries were those in which the nature was most bountiful, and now the richest countries are those in which the man is most active. Our world has been divided into three categories of countries: developed countries, developing countries, and underdeveloped countries. The yardstick which has been used to divide them is the construction for economical development. And there cannot be any development without disbalancing the existing eco-friendly environment. In some cases, this disbalance is more, in other cases, it is less. If the development is more and its impact on the environment is less, then it may be called as a meaningful development. It is acceptable to every individual in the society, and generally such tendency prevails in the developed countries and in some developing countries also. But if the development is less and its impact on the environment is more, then it is not a welcome development, not acceptable, and generally such tendency prevails in the underdeveloped countries and in some developing countries also. Engineering geology is playing a remarkable role in taking a balanced view of the situation, balanced view of the development and its impact on the environment, and then suggesting a techno-economical path to the construction agency to execute the project accordingly. In the case of Chennai National Highway Tunnel, we could maintain an eco-balance between construction of the tunnel and the surrounding environment. We have a mighty river Chenab near the north portal. We have another mighty river Tavi near the south portal. But we did not throw the excavated material of the tunnel in these two rivers because there are many reservoirs located in the downstream of these rivers of some hydroelectric projects, and which have been already silted up. So by throwing this excavated material, it would have added more siltation in the reservoir. For instance, Slal hydroelectric project in the downstream on Chenab River is already silted up by more than 70%. So what we did instead of that, we discovered those valleys in the vicinity of the tunnel which were carved out or formed by the flash floods or cloud bursts recently, and they had eroded a considerable part of the land which was otherwise being used by the locals as for their horticultural purpose or for agricultural activities or for grazing. So we retrieved that land by depositing such excavated material of the tunnel on both slopes of the valley with proper compaction, with proper angle, and provided the toe support also to these slopes and made fit for the use of the local people. This was admired by all the people around, even the district authorities of Udaipur also. Chennai National Highway Tunnel is the longest highway tunnel in our country till date, with a length of 9.2 kilometers. Its width 9.35 meters, vertical clearance 5 meters, and it has a raw cover of more than 1 kilometer above the central part of the tunnel. This tunnel has been excavated within sedimentary rocks of interbedded sequence of hard sandstone, medium siltstone, and soft grey stone, with a variability in their thickness, variability in their geological properties, engineering characteristics, in their rock mass classifications, in their stand-up time and support system, and their uniaxial compressive strength. The average uniaxial compressive strength of hard sandstone of Chennai Nashi Highway Tunnel is about 80 megapascals, medium siltstone about 40 megapascals, soft clay stone about 20 megapascals. 1 megapascal is equal to 10 kg square, 10 kg pressure on 1 centimeter square. Originally, these rocks were deposited in a shallow sea conditions about 40 million years ago in the Himalayas. We call such deposits as estuarine deposits. We call these rocks as Murris. Murri is a famous hill station in Pakistan where these rocks are exposed on a very large scale, both in space and time. It's here that the rocks were first studied by the Britishers about 170 years ago. Since then, much detailed work has been carried out by the officers of the Geological Survey of India to find out their geographical distribution along these mighty Himalayan ranges. And it was discovered that these rocks have their extension right from Pakistan in the northwest to the northeastern states of our country, such as Assam, Arunachal Pradesh, and Nagaland. Even their further extension has been traced towards Myanmar country in the east and Afghanistan country in the west. Width-wise, these rocks are confined between two major tectonic planes, Murray Thrust in the north and main boundary fault in the south. The distance between these two tectonic planes varies from place to place. In Chennai Nashi Highway Tunnel, these two tectonic planes are about 40 kilometers far from each other. Murray Thrust is about 5 kilometers away from North Portal, and main boundary fault is about 25 kilometers far from our South Portal. So tunnel is safely located between these two tectonic planes, and it does not intersect any of them. Different names have been given to these rocks at their different geographical locations. In Pakistan and J&K, these are popularly known as Murris. In Himachal Pradesh, as the Dikshai formations, Kasoli formations. In northeastern states, Tipam sandstone, Girijan clay. In Myanmar, these rocks are called as Pigu series. Even the rocks equivalent to Murris in European countries are known as Baradi-Gallian rocks. So these rocks have global distribution for thousands of kilometers, but in spite of that, these rocks have remarkable similarity in their lithology, structure, tectonics, and mineral economics. These are the rocks which have a strong affinity for oil and gas reserves. All our oil fields in the northeastern states, such as Digboi oil field, have their source in these rocks. Many oil fields, many major oil fields in Myanmar country have their source in these rocks. Even the famous gas springs of Geology Temple in Himachal Pradesh state have their source in these rocks. And many oil fields in Pakistan and few in Afghanistan have their source in these rocks. So these Himalayan ranges are the richest sources for mineral wealth, oil and gas reserves, and for hydropower potentiality. But in addition to that, these Himalayan ranges has also provided the inspiration to human mind to understand the metaphysics and divinity in the life, and for the geologists to understand the geological processes and the mechanism which was responsible to raise these mountains up to their present heights. On the other hand, Afghan India Friendship Dam is the highest earth and rock-filled dam in Herat province of western Afghanistan. 106-meter high dam, 551 meter long, and has a reservoir of about 25 kilometers in a broad river valley, which is about 3 kilometers in width. This is a multi-purpose dam mainly for agricultural activities and irrigation facilities. I am sure the House is well aware of the inherent benefits of hydropower plants and dams with their well-established technical and economical advantages. This dam was earlier known as Salma Dam Project. Salma is a small village near the dam axis, and after the completion of this dam, now it is known as a Afghan-India Friendship Dam because this dam has been constructed free of cost by Government of India for the people of Afghanistan as a goodwill gesture and friendship. Dam has been constructed across Hind Kush, across Hari Rud River Valley, a Hindu name. This valley is also known as Muhammad Gauri Valley. Muhammad Gauri, a renowned Muslim king in the past, he used to visit this beautiful valley frequently and had camped many a times on the bank of this river. Now all those things are under the submergence of the reservoir of this dam. The rocks which have been intercepted in this dam are very hard and competent, igneous and metamorphic rocks. Some of them are gneisses, schists, quartzites, tonalites, granophytes, taschenites, thyrolites, marble bands. Tonalites has been formed by the differentiation and protonic crystallization of primary granodiorite granite magmas. Granophytes has been formed by differentiation and volcanic crystallization of primary thoriatic magmas, and taschenites, thyrolites were formed by differentiation and volcanic crystallization of primary alkaline olivine basalt magmas. These rocks are about 1000 million years old in the offshoots of Hindu Kush mountain ranges. Both these projects, that is Chenani hydroelectric projects, Chenani Nashri Highway, Chenani Nashri Highway Tunnel, as well as Afghan India Friendship Dam, were constructed, investigated, constructed, and then inaugurated by our Honorable Prime Minister Shri Narendra Modi in 2016 and 2017. Friends, after working for about 100 engineering geological projects in the country as well as abroad, in Afghanistan, Ethiopia, DR Congo, Burundi, Rwanda in South Africa, Laos, Myanmar, Nepal, Bhutan, I got many opportunities to interact with the international experts in the field of geotechnical engineering, such as Nick Barton, who has provided us Q value system, Marcelo, Andia, Valentine, Ramana. So these are the leading geotechnical engineers in Spain, and my interaction with them has definitely broadened the horizon of my professional field of engineering geology to keep it at par with the international standard. And every excavated tunnel, whether it is a highway tunnel, railway tunnel, or hydropower tunnel, and whether it has been excavated in Himalayas or in any other mountain system in the world, it has provided a new opportunity to understand the new techniques for the tunneling. And every aspect of the constructed surface and subsurface structures uh, has deeply is deeply influenced by the geology of its foundation. Thus, the reliability of the forecast geology plays a very important role, and it becomes mandatory to carry out detailed geological study for such structures right from the investigation stage up to the completion of the structures, because such studies not only provide the foolproof safety to the structures for longer period, but also improve the quality of the construction of the project within stipulated time period and without overrun of the cost. About the rocks of the Chenani Nashri Highway Tunnel. These are the rocks in which the maximum tunneling has been done in the past during the Britishers' time, while they were constructing some railway lines across these ranges in the northeastern states, in West Bengal, in Himachal and Punjab. While constructing a 96-kilometer long narrow gauge railway line from Kalka to Shimla in Himachal Pradesh, 103 tunnels were excavated in these rocks. But all of them are much smaller in length and width in comparison to the Chennai Nashri Highway tunnel. The longest one is only 1.2 kilometers, known as Budog Tunnel, named after Colonel Budog, a British civil engineer by profession. And rest all the tunnels are less than 1 kilometer in length. Colonel Budog was the main architect of this tunnel, but unfortunately he committed suicide in this tunnel after the excavation of this tunnel. It so happened that the tunnel was being excavated from both the ends under his supervision, and when the excavation finally reached at the midpoint of the tunnel from both sides, the tunnel axes did not match with each other. There was slight error in that. So on this, the British government imposed a fine of ₹1 on Colonel Budog. He paid the fine gladly, but then committed suicide in the tunnel. A great tragedy indeed. Anyway, although these tunnels are smaller in size, but these have established a history of successful excavations by virtue of which all of them are still intact and have been standing for the last about 120 years without any question mark on their stability. A great achievement indeed. And kudos to all those engineers and geologists who were associated with the excavation of these tunnels. And obviously, this has raised the level of confidence in us for future tunneling in the Himalayas, and Chennai Nashri Highway Tunnel is one of such ventures with which we were actively associated for its construction by an Australian company under our supervision. The excavation conditions in Chennai Nashri Highway tunnels are very similar to these railway tunnels of Himachal Pradesh and J&K. Most of these railway tunnels have the same alignment and same intersection angle with the geometry of the rocks as we do have in Chennai Nashri Highway tunnel. Even the status of the geological parameters which are required for the evaluation of the rock mass class and spore system is also same. And we were very lucky that we did not intercept the serious excavation problems in Chennai Nashri Highway tunnel, which is an unbelievable fact. Otherwise, tunneling in Himalayas has always caused serious hazards and unfortunate human sufferings. But this tunnel has raised the level of confidence in us by virtue of which we are now more competent to excavate any length of tunneling in these mighty Himalayan ranges for the future upcoming projects, whether these projects are related to the four-laning of the national highways or extension of the railway line or for any hydroelectric project. But at the same time, we should never rule out totally the possibility of the occurrences of sudden geological surprises and interception of hidden groundwater bodies till we trigger the last blast in the tunnel. This I am speaking so because we had faced very serious excavation problems in one of the railway tunnels on Udhampur-Katra railway section, and that caused us tremendous loss of time and money. It took extra years and extra crores of rupees to complete the excavation of that tunnel, which was hardly 3 kilometers in length. And the rocks and their geological properties and engineering characteristics were same, which we have faced in the Chennai Nashri Highway tunnel. Though I was never associated officially with the excavation of this tunnel, but it was given to understand that the major cause of failure was the unfavorable tunnel drive direction with respect to the geometry of the rocks. In other words, tunnel axis was exactly along a major tectonic fault, and then we did not install the support system timely within the stand-up time of the rocks. So basically, these rocks are very good tunneling media provided you install the correctly evaluated support system timely today. Otherwise, tomorrow it will be too late to correct our mistakes. Now, to find out the correct support system in the tunnel, you need to know first the correct rock mass class. To know the correct rock mass class, you need to know first the correct assessment of the geological parameters from the tunnel phase after each blast. And to assess these geological parameters correctly, you need practice, you need experience, and this comes gradually. by devoting your more and more time inside the tunnel as well as outside the tunnel to understand very clearly the three-dimensional position of the rocks in the tunnel and correct geometry of the structural discontinuities, which is the backbone of all the rock mass classification schemes. So there is a positive link between geological parameters at one end and support system in the tunnel at the other end, and this chain should never be broken in at any point of time in order to obtain correct class and support. And if it is broken, then you cannot find correct results from all these rock mass classification schemes, and there will be controversies among us whether the rock at the tunnel face is good or bad for its excavation behavior. And friends, today the most difficult task being faced by the designers is the lack of the quality of the input field data on which is based the design of the structures in the rocks. It is therefore very important that the quality of the input field data should match the sophistications of the design methods. In other words, if you have not measured correctly the length of the foot, this means you don't have any yardstick with you to measure any parameter, whether it is related to geology or civil engineering. Now, as per the concessionaire agreement between the Government of India and international contractor, it was decided to apply only NATM classification for the rocks of Chennai Nashri Highway Tunnel to find out the support system. NATM is an acronym. Its full form is New Austrian Tunneling Method, and it is one of the most popular rock mass classification schemes in the field of geotechnical engineering. Other similar popular rock mass classifications are GE Beacom's RSR classification 1972, ZT Winaski's RMR classifications 1973, Nick Barton's Lion Lune Q value system 1974, D.A. Williamson 1980, Cumming 1982, Kandorsky 1983, then coal mine roof rating classification by C. Mark and G. M. Molinda 1994, Palmstrom Bruch 2006, and the latest one is Russo Grasso from Italian Geodata Center, their multiple chart system. All these rock mass classifications are based on the geological parameters to find out the support system in the tunnel. And these geological parameters are assessed by the engineering geologist from the face of the tunnel. He evaluates the support system which is needed for the tunnel, and he passes on this information to the site engineer, and he in response install that support system in the tunnel. So a casual approach by the geologist to assess these geological parameters would cause disastrous result, which is a threat to the stability of the tunnel. And even if the geologist has very correctly evaluated the support system, very correctly assessed the geological parameters, but that support system is not installed by the engineer timely within the stand-up time of the rocks, even then the results will be disastrous. So a perfect coordination between the site geologist and site engineer is the most essential requirement for successful excavation of tunneling. NATM was basically developed between 1957 to 1965 by many geotechnical engineers such as Repsebix, Lofer, Pacher. The main idea of NATM classification is to stabilize the tunnel itself by using the geological properties of the rocks surrounding the tunnel. Thus, NATM is not a set of specific excavation or specific support technique. It is a philosophy where geological properties of the rocks and the support system are integrated into a ring-like support structure. Thus, rock and sport becomes a part of the sporting structure, and based on the experiment experience, this philosophy has been named as a Netum classification. Netum has a many techniques for safe tunneling in those rocks in which the stand-up time is limited before the rock mass failure occurs. And these techniques are to go for the small stretches of heading and bench method for small dia tunnels, and to go for multiple drift method for large dia tunnels. These techniques are applicable to these soft rocks such as shale, phyllites, mudstone, in which the possibility of squeezing and swelling is there. Uh, no, according to Netum classification, 90% rocks of the Chennai National Highway Tunnel are B1 class, 6% B2 class, and 4% class C. Broadly, Netum has been divided into three categories A, B, C. In class A, we get stable conditions of the rock, stable to or breaking conditions in the tunnel. In class B, we find friable to rolling conditions, and in class C, we find rock bursting, squeezing, swelling, flowing, every type of difficulties there. So 90% rocks are B1 class, means friable rock. From fair to good category rock, there are minor deformations which decline rapidly. There is structural weakness in the rock mass, and blasting operation leads to loosening and separation of the rock blocks from the crown and upper walls of the tunnel. Round length is governed by the stand-up time and stand-up length. Stand-up time of these rocks is 10 to 15 days. That means you have to install the evaluated support system within this period. And if you fail to do so, there are chances for the tunnel collapses. Cohesion values for this rock is 250 kilopascals, 1 kilopascals, 10 gram pressure on 1 centimeter square. Friction angle is about 30 degree for a span of 5 meters. I have also tried to use RMR classification of Z.T. Binaski and Q value system of Dick Bartons to these rocks also, in addition to Netum classification, just to know the variability in their resultant values. And I have found that average RMR value for this B1 class is about 50, and average Q value for this class is 10. 6% rocks are B2. B2 means very friable rock. Range is from fair to poor. There is a poor interlacing and poor structural strength, and blasting operation leads to rapid deep loosening of the rock mass in the tunnel. And this round length is governed by the stand-up time and stand-up length. Stand-up time of these rocks is 10 to 15 hours. So install this board within this period. Cohesion values about 150 kilopascals. Friction angle about 20 degree for a span of 2.5 meters. Average RMR values for this is 30, and average Q value 4. 4% rocks of Chennai National Highway Tunnel are class C. Poor to very poor category. Unpredictable rocks, sudden releases of the stresses and causes the rock bursting, squeezing, swelling, flowing condition. Every type of difficulty is there. It is very difficult to excavate them, very risky to excavate them. It takes much time to excavate them, and maximum accidents happen only in these rocks. There is no stand-up time. Immediate you need support and rich support. Rich support means that if you are installing steel rib or steel set or lattice girder, very closely spaced should be installed. Even rib to rib support sometimes is needed. Shotcrete, thick shotcrete, whether plain shotcrete or steel fiber reinforced shotcrete. Even rock bolts should be placed at very close interval. The average cohesion value for these rocks is about 90 kilopascals. Average friction angle is about 10 degree for a span of 1 meter, and then RMR values for this is about 10, and then Q value is 0.5. So ladies and gentlemen, these are the geological and geotechnical studies which we carry out for the engineers in their field for their structures. And with these words I stop here. I am very thankful to all of you for your patient listening and giving me opportunity to share my views with you. I am very thankful to my Department of Applied Geology, worthy members of the organizing committee, head of the Department of Applied Geology, Honorable Vice Chancellor of this university for their collective decision to nominate me for this prestigious award, and trust this will be the highest degree of honor for me. And this occasion has really taken me 50 years back when Professor West Sir had awarded me the Best Student Medal and Certificate of this university in the annual function of 1970. So long live this Sagar University, and my profound venerations to my teachers and elders, love to younger generations, and finally goodbye to all my listeners. Namaskar.